Hello, and welcome to this lab on solubility and solubilization. You may take it for granted when you take a liquid medicine that the drug in there has been dissolved or suspended. However, it can take some thought to actually get that final formulation developed. If we want to make a solution, that is where our drug is dispersed on a molecular level through our liquid suspension, we have to make sure that it will dissolve in some part of that liquid formulation. In this lab, we're going to look at how you do that with aspirin. So aspirin is a drug that people are probably very familiar with and maybe have taken as well. And you may have taken a liquid formulation, or you may have taken a tablet which is dispersible in water. But actually, aspirin's solubility in water isn't necessarily that great. And so in this lab, we're going to look at ways of improving that solubility after having first determined what its solubility is as well. And one of the ways that we're going to look at, in fact, the way we're going to look at improving that solubility is by using a surfactant. A surfactant is a molecule that has two halves. It has a water-loving hydrophilic part and a water-fearing hydrophobic part. When you put surfactants into water or other solvents, but in this case water, what they do is try to arrange themselves to hide the water-fearing part, the hydrophobic part, from the water, and to expose the water-loving, the hydrophilic part, to the water. And what that means is that when you put a surfactant into water, first of all, it will coat all of the outside areas of the water, so the surface and where it touches other parts of a container. You'll have the hydrophobic part either poking out of the water or touching the container, and the hydrophilic part shielding that, facing into the water. Once all of those surfaces are coated and you put more surfactant in, there's nowhere else for it to hide that hydrophobic part. So either it has to not dissolve or it has to do something with that hydrophobic part. And what happens, because it has the hydrophilic part as well, is that lots of those surfactant molecules will come together and will form something called a micelle. And that micelle is an arrangement of those surfactant molecules which aggregates all of the hydrophobic parts together in the middle and then surrounds itself in a ball with the hydrophilic parts. And so those hydrophilic parts are shielding the hydrophobic parts from the water. And when you get past the point at which there's still surface or still a container to be coated by surfactant and start making those micelles, that's a critical point, and it's when micelles start forming, and so that's called the critical micelle concentration. You may also see this as the critical aggregation concentration as well. And once we go past that point, you start to form micelles. And this is the point where you want you to get your washing water past. You want to get your washing up liquid into your water past the critical micelle concentration so it can start to form micelles in the water. And once you've got micelles in the water, you've started to create new environments in your solvent within which you can start dissolving things. And that's exactly what we're going to do with the aspirin. We'll have created new environments in there. We'll have the water, but now we'll also have the hydrophilic head part of micelles and the hydrophobic tail part inside of those micelles as environments for things to be dissolved in. And if we take the example of washing up liquid, that's exactly where your oil and your dirt will go into, and that's what makes your washing up water with washing up liquid in far better than just using warm water on its own. So take a look at the lab book, and then we'll move on to doing the practical part of the lab. In the first part of the practical, we're going to determine the solubility of aspirin in 4 different dissolution media. Those media are just deionized water, which I've got in a little beaker here, and then deionized water with 0.1% sodium dodecyl sulfate, 1% sodium dodecyl sulfate, and 4% sodium dodecyl sulfate. Now, in the introduction to this lab, I mentioned about going past something called a critical micelle concentration, and you'll be able to see that that's what we have done in all 3 of these solutions. So sodium dodecyl sulfate is a very common surfactant. You will have used it, I guarantee you. It's in most washing up liquids, most shower gels, most laundry liquids, and so on. So most liquid detergents that you use at home will have sodium dodecyl sulfate in it. And you really don't need a high concentration to get past that critical micelle concentration. And a really easy way of telling if you're past the critical micelle concentration is to just look as to whether you're forming bubbles or not. So you can see here, even in the 0.1% solution, that I've got some bubbles at the top, and if I shake it, you'll be able to see those more clearly. So that indicates that we've gone past the critical micelle concentration because we've got excess surfactant in there that's not coating the container, so it's able to reduce the surface tension and create bubbles as well. Incidentally, the critical micelle concentration is dependent on the vessel that you put it in as well, so it's a very specific thing for each container you may be in, depending on how much surface area is exposed to the water. So all of these media, except for the water, have gone past the critical micelle concentration for sodium dodecyl sulfate, but they will have increasing amounts of those micelles in them with the increasing concentration. So the way we're going to determine the maximum solubility is to ensure that we saturate all of these solutions with aspirin. So we're going to take a small amount of aspirin and the solutions and put them in these plastic tubes. And what we'll do is put a known excess of aspirin in there. We know we're going to saturate the solution, and then we'll leave them to mix for 40 to 45 minutes, so we know we've got as much in there as we can, and then we'll filter off the excess and take a UV vis reading to see how much aspirin is in solution. And whilst that's mixing, we'll have to make a calibration curve to determine what an absorption on the UV vis means for the concentration of aspirin in those solutions. So I'll get on with this. So the first part is we're going to weigh directly into these plastic tubes, and I've got an already zeroed and level balance here. What I'm going to do is I'm just going to put my, actually with the lid, I'm going to put my plastic tube on there centrally, and then tare or zero the balance with that on. This means that I can weigh directly into the tube, and I don't have to worry about losing any of my mass when I transfer between a weighing boat, for example, and to the tube. And looking at the script we've got, I'm going to put 200 milligrams of aspirin directly in there. Now this will require me to take it off the balance, and with a clean spatula I'm going to have to put some in, see how much it weighs, and then come back and do that as an iterative process. Now I'm not going to put the cover on each time. I'm going to put the cover on when I get close to the final value, so I know how much accurately I've put in. So I've got 70 milligrams with that, so I need to do about 3 more of those. So that's how I sort of work out how much I'm putting in. And if you make a note of how much you put in with one spatula full and how much that weighed, it makes it quicker for you to then weigh out roughly to the right amount, knowing how much each spatula full will put on as a mass. Let's try and get that in the middle. Okay. And it's always better to be cautious with how much you put in, rather than put too much in, because once I've taken this solid out, I don't want to then put it back in for risk of contamination, just in case this tube isn't as clean as I think it is. That's just good lab practice. Okay, so I haven't been cautious as cautious as I should be. So I'm not going to put it back into the sock bottle. I've got a little weighing boat that I've got here ready to get rid of any excess, and then I'll put that into the solid waste bin at the end of the lab. I'm just going to tap a little bit out and see how that is. Now, there we go, that's fine. So that now reads 0.0 0.204, which within the area of this balance is absolutely fine. Now I'm being very accurate here, but you may think, well, what's the point? And you might be correct. As long as I've got over 200 milligrams and I'm around 200 milligrams for all of them, then it's not really important because we're just trying to saturate, aren't we? So we're just putting a known excess in to make sure we get to the maximum solubility, the maximum amount of aspirin dissolved in these solutions, so we're at saturation. And you'd be right in thinking that, but I'm just going through this methodically. So I've got that in there, and I now need to add, following the script you've got, 3 millilitres of the dissolution medium. And this one I'm doing first is water. I would normally lift this up, but for the sake of the camera, I'm going to bend down and measure this on the bench so you can see what I'm doing. That's pretty much perfect. So this is the water that's at 3 millilitres, and if I can get that level roughly with the camera, if I can get it level somewhere, there we are. You should see that the bottom of that meniscus is level with the number 3, indicating I've got 3 millilitres of water in there, which I'll now transfer to the plastic tube. Just make sure it's all out, particularly with low volumes in small measuring cylinders. Water has a high surface tension. It will have less when we do the ones with the surfactants in. We need to make sure we get that out there now. Okay, so now I need to make sure this is on very securely, because what we're going to do now, so I don't have to stand here for 4 to 5 minutes and shake it, we're going to put these into this rotary agitator. And that will go around like a little Ferris wheel, and I'll be able to leave it for 4 to 5 minutes. So what I'm going to do now is I will do the same for the other 3 dissolution media, and you don't need to see me doing that. And then whilst they're going around, I'll then go through with you how we're going to make the calibration curve to measure the how much aspirin's in each of these solutions afterwards. I now have all 4 solutions rotating there, so they're being agitated and mixed. So that's with water, 0.1, 1 and 4% sodium dodecyl-sulfate. Now what you didn't see me do is that I labelled all of those so I knew which one was which when I took them off, because if I didn't, I'd have to start again because I probably wouldn't be able to tell the difference between the 3 of them. So now they're mixing. When they're done, we're going to want to be able to determine how much aspirin is in each solution once we've filtered off the excess. And to do that, we're going to use the UV-Vis spectrometer, and we'll dilute the solution, put it in there, and we'll get an absorbance reading. But the absorbance reading on its own is no use to us. We need something that tells us what does that absorbance reading mean. And what we'll create as that decoder is a calibration curve. So in there, we will have solutions that we will know the absorbance of once we've taken the absorbance reading. And we need to know what concentration does that correspond to. So what we'll do is the reverse. We'll make multiple concentrations of aspirin solution, known concentrations of aspirin solution, that we don't know the absorbance of, take their absorbance, and then note them down. And then we can plot those with the concentration on the x-axis that we know because we've made them up, and the absorbance that we know because we've tested it in the spectrophotometer on the y-axis, and plot our results. If we then put a line of best fit through those, which in this case will be linear, we can use the equation of that line to then tell us what is the concentration of our unknown solutions, and therefore what is the maximum solubility in each of those, because we know that they're saturated solutions. I do a more detailed explanation of this in the labs from first semester if you want to go back to those. So what you did in the first semester is you made up multiple separate concentrations of your known ingredients. Now that is fine to do, but what we're going to do in this lab is another way of doing that, another way of getting all of those concentrations where we only have to weigh out stuff once. And that's called a serial dilution. So we will weigh out enough aspirin to make our most concentrated solution. which in this case is 80 milligrams per litre, but we're only going to make 100 millilitres of it. And then we'll take some of that known concentration and we'll dilute it by a set amount. And we'll have a second known concentration. And then we'll mix that up and then do the same process again. We'll take some of that and dilute it with a known amount of water, and then we'll have a third known concentration of aspirin in water. So we'll do that 4 or 5 times, and then we'll have all of the concentrations we need, having only weighed out once. And that's called a serial dilution. So the most concentrated solution is 80 milligrams per litre, and we're going to make 100 millilitres, so we need to weigh out 8 milligrams. Now, I've previously tared this. I would put it straight into the beaker, but we're really at the limits of what this balance can actually do. And so I need to make sure that I'm not overloading the balance with the beaker so it can accurately weigh down to 8 milligrams. Now, this is a very small amount that we need to put on. So you'll see that I'm literally just tapping it out onto the balance. And I've got very lucky there and weighed out exactly 8 milligrams. That is very fortunate for the recording. So we'll get rid of the aspirin now, and I need to put that into 100 millilitres of water. And so I'm going to do that in a beaker, make sure I get all of the aspirin out, because it is small amounts we're talking about here. So any slight error is a big percentage error, so we need to be careful. And then I've previously measured out 100 millilitres of deionised water, which I'm just going to put in here. And then I'm not going to use that same spatula to mix this, because it might still have aspirin on and it'll affect the results. I'm going to take a clean spatula and mix this round. Now I need to make sure that this is all fully dissolved before I move on to diluting it, because otherwise I'm not diluting the correct strength. And I can still see that there are aspirin crystals in there. What's important to think about here is we've obviously done a bit of prep work to know what concentrations are needed. And you will have noticed that I've put 8 milligrams into 100 mils of water here. And we put 200 milligrams into 3 millilitres for our saturated solutions. And so just by that, that's a clue that we put in way, way, way more than was needed, as we said we would. And you know that it's not going to be that soluble, because we're having to put 8 milligrams in 100 millilitres of water to get a calibration curve in roughly the right area for what the actual solubility is going to be. So logically, and just by thinking about it a bit, you'll be able to work out that we're not going to be talking about a very soluble material here. Now this is going to need a little bit more stirring before it's dissolved, and so I will stop the video and restart once it's all in. The 80 milligram per litre solution is now dissolved, so we have our highest concentration of aspirin solution there. And so now I need to do my serial dilutions. So I need to measure 2.5 millilitres of this solution. So I'm just doing it at eye level. Yeah, 2.5 millilitres. And then I need to put in 7.5 millilitres of water to that to make it up to 10 millilitres. So what I'm going to do is make that up to 5 in this measuring cylinder. I'm going to pour that into the next beaker, which I've already labelled as solution B. And then I'll measure out another 5 millilitres. another 5 millilitres to make that up to its final concentration. I'm going to leave that pipette with the water there, and I'm going to get another 5 millilitre measuring cylinder, make sure this is all thoroughly mixed, and then do a serial dilution. So we're going to dilute that again. So this is, we're diluting by 4, because we're taking 1 part to 3 parts, and I'm going to get that to 2.5 millilitres. Again. Okay. And then again, we need to have 7.5 millilitres of water. So I'm going to take that up to 5 millilitres, put that into the beaker that's labelled for solution C, and then measure another 5 millilitres to make it up to 10 millilitres. Okay. And so, again, we'll do that one more time. Don't need that last beaker, we're only going to do that one more time. Just making sure this is fully mixed. I'm going to take 2.5 millilitres to do the final serial dilution, which is much quicker than doing them all separately. Weighing each one out, waiting for it to dissolve, etc. So now another 5 millilitres to make this up to its final dilution. Hope I've got enough water. Almost enough water. We've now got 4 solutions with which we can do our calibration. And to do that, we need to have the UV vis set up, and we need to blank that with water, because that's the solvent we're using. And remember, when we blank a UV vis, we're telling the UV vis basically everything, the absorbance from which to ignore. Everything the absorbance from which to ignore, which includes the cuvette and the solvent, because we're only interested in the concentration of the aspirin. So I'll put that in there. I've already set this up to 229 nanometers. And take a 0, there we go. And just to check that, we'll take the absorbance of our blank, our 0. And you may see a tiny fluctuation. I've got minus 0.002. So we can see that that is within just the fluctuations of the instrument. And so I can fill in on the script that the blank UV absorbance is 0. Okay, so that's all set up. Now we need to go through all of our different solutions. Now I'm going to start at the lowest concentration, because that means I can use the same plastic pipette to fill all of them. Because if you go from low to high, you're not going to be contaminating the lower concentrations with the higher concentrations. You may slightly dilute these ones, but as long as you clear out the pipette fully, you're generally absolutely fine. So we'll start with D, which is the 20 milligram per milliliter concentration. Fill that up, get that into the UV vis and press green to go. And I'll move on to the next solution. So now we've got the results for our calibration curve. What you need to do is, as I said, there's a piece of graph paper in here, or you can do it on Excel, is plot the concentration along the bottom and the absorbance along the y-axis. So concentration on the x-axis, absorbance on the y-axis. And then with that you'll be able to determine concentration of our unknowns. So from here we can now move on to actually looking at what we're doing with saturated solutions, and so once they're done we'll come back on and I'll go through that. It's now been 45 minutes, in fact even a little longer, that my tubes with aspirin and different dissolution media have been spinning on the windmill over there. So they're now ready to come off and be analysed. Now you can see that we clearly still have got aspirin left in the bottom or at the top of all of these. So we know that we're pretty sure that we've saturated the solution, although in some cases you may need to mix for longer than that, because whilst dissolution may be spontaneous, it isn't necessarily quick. And of course this is going to be the maximum solubility at room temperature. So following your scripts, what we're going to do now is we're going to filter off all the excess aspirin, and we're going to do 2 dilutions so we get that concentration down into the area that our calibration was in, just to be sure of it. And so the way we're going to do that is we're going to take a glass funnel, and that will go in to a volumetric flask, the first one. I'll do this closer to the camera. And then we'll put a cone of filter paper in the top and just pour it through and let it all drain through. Now we don't rinse this through, because if we put any more solvent through we'll dissolve more aspirin and we'll also dilute the solution, so it's not going to be saturated. So we don't do that. We want to know the dilution that we're doing, and we don't want to bring any more of that aspirin through. So to make a cone of filter paper, you take a circle of filter paper, and then one of the ways of doing it is to fold the filter paper in half, and then to fold over another section, like so, smaller or larger depending on the funnel. Then you can open it out again, and then you can use those pre-folded lines to make a flip back in on itself to make a cone. And then you may need to adjust that to get it to the right size to fit into the bottom of the funnel. So you can see that's too large, and we need it to be smaller to fit into the bottom of the funnel. So I'm just going to fold that over a little further than it was previously, until we get to something approaching going into the bottom of the funnel, like so. And then we'll pour the tube through into the volumetric flask. Now these are very small volumetric flasks, so if you just put that in and let it drop, you make a seal at the top, and so the air has nowhere to escape and we may not be able to pour in. So what I'm going to do is I'm going to hold the funnel loosely in the top, like so, whilst I pour into the cone of funnel paper. Now I'm going to do this with just one on the video, and I'm going to do that with water, but the same process will be repeated with this and with the dilution for all of them. So just pour this, make sure it goes through the filter paper, and then it doesn't go over the tops and sides of the filter paper. Now this will be a relatively slow process. If it was larger volumes, we may use something called vacuum or Buchner filtration to do this as well. But it's a small volume and it's already nearly gone through. So this tube's now empty, and that will go into the solid waste. And we just wait for this to fully drain through. You can see I was making a seal with the water at the top, so I need to just allow this to drip out. And you may need to break the surface tension by just tapping the funnel on the side of the volumetric. And then we've allowed that to fully drain through. We may allow a little longer to be completely accurate, but we'll just stop there for now. So we can then put that to one side, and we need to do the dilutions to get this into the ballpark area of where we're going to actually be able to take a reading on here. Remember how much you've diluted it and by the factors by which you've diluted it, because once you've worked out the concentration from here, you then need to multiply whatever the answer is to get what the original concentration. So we're going to be working out the concentration of the diluted sample, and then we need to just use the same factors to go back to what the original sample was after. And so I'm going to need some deionized water. Enough to dilute to 10 ml, then take a sample of that and dilute that to 25 millilitres. So I'll get a clean pipette. And remember, with a volumetric flask, we only do one measurement in a volumetric flask, and that is the measurement that it was made for, which is up to the calibrated line on the neck. So we need to look at that accurately, make sure that it's lined up, the back and the front of that line. You can only see one line, and then bring that up to just touching. The bottom of the meniscus just touching that individually calibrated line. And then, something on there, we need to mix it. So we put our thumb on the lid, and we do some inversions, ensuring that the air bubble actually goes around. Okay, because otherwise we might not get mixing up into the neck, and that's where we're going to be taking our sample from. So that's the first dilution done. That was 3 millilitres diluted to 10 millilitres. Okay, so that's the first thing to remember. And then we need to take 0.5 millilitres of that solution and place it into another 25 millilitre volumetric flask. Right, so I've got a clean measuring cylinder here. Yeah, but we can't accurately measure 0.5 millilitres with that. So what I'm going to do is use a glass pipette, and remember, when we put these in, we hold the glass pipette as close to the top as we can, and then we secure it in there nice and tight, but we don't push from further down because we can break these very easily, and we don't want to cut ourselves accidentally with them. Just checking that that was clean. So I'm not going to be able to get this into the volumetric flask, but we've already mixed it, so I can just decant that into a small beaker, so I can actually get my pipette tip into there, and that's going to go into there, but we want 0.5 millilitres. Which I can accurately measure out this. Put that in there. Great. And I'm going to take that off because I don't need it now. Like that. And then I need to dilute this to the line that we've got there. Now I will do the last bit with the pipette, but I'm just going to get us to that line, close to that line, by pouring. And I'm going to need just a little bit more. There we go. Perfect. So that's just water, I'll leave that there. And we need to mix this again. So we have a homogeneous sample. And remember the dilution for that. So that was another 0.5 to 25 millilitres. So that's a 50-fold dilution. And then, with a clean plastic cuvette, a clean disposable pipette into a clean plastic cuvette. I'm going to take a sample of that. And get a reading. And this is already still zeroed to water, and it's at the right wavelength, so I should be able to take a reading from there and see that the absorbance is 0.726. 0.726, but we're going to take 3 readings. 0.723 and 0.721. Fine, they're all pretty close, and so we'll take an average of that, which will be somewhere around 0.723, and then repeat that for the other 3 solutions. And once I've done that, we'll then be doing the analysis where we plot the calibration curve, and then we can use that calibration curve to determine the drug concentration, and then we'll look at we'll be able to say maximum solubility and classify the solubility according to the British Pharm Compare. So I'm now out of the lab, and as you can see, I'm back home to do the little bit of analysis and sort of contextualization of why this sort of thing is important. Always a good idea to do that outside of the lab in a more relaxed and comfortable environment. So what I'll do is I'll share my screen with you, which has the spreadsheet of all of the results on, and you also should find you have the results on the relevant folder online, or they are just in the video earlier, and so you can note those down if depending on how you're viewing this and what you've got access to. So I'll just share my screen now. So what we need to do is we need to plot the concentration, our known drug concentrations on the x-axis against our known absorbances on the y-axis. And we're going to do that with a scatter plot. So just going to put that in, and we can see that just over here. So we've got a nice linear relationship that we can see. But what we want to know is what that relationship is. So how do I get from an absorbance to a concentration in milligrams per litre? And you can do that by hand, and you can work out the gradient of this line by hand. But as we're on Excel, then we may as well just get Excel to do that, and it'll probably be more accurate. So we're going to put a linear trend line on, and double click on that, and get it to show the equation on the chart. I'll just make that a bit larger. There we go. There we go. So we can see the equation there. We can also get it to show the R² value, which is a measure of how good a fit this is. I'm not going to put that up because you don't need to worry about it, but you would if you were unsure as to how good a line of best fit that was. So we can see here that Y, so the absorbance, equals 0.0297 times X, the absorbance, minus 0.003. Now this should go through the origin. That is just a little bit of error in our readings. And so I'm going to just ignore that and make it negligible. It is negligible, so we're going to ignore that. Now this maps exactly onto the Beers-Lambert law if we remember that the path length is 1 centimetre, but I've been through that before. So if you still want to go through the Beer-Lambert law and how that fits on, go back to previous things you've been taught from me. So we want to use this. Essentially the formula is Y equals 0.0297X. We want to use that to determine X for known values of Y. And so, of course, to get x, we will do y divided by 0.0297, and that will give us our value. And so that's exactly what we need to do up here. Now we have that. So the concentration for this absorbance reading of 0.72 is going to be equal to 0.72 divided by 0.0297. And we get a concentration of 24.24 milligrams per litre. And then we need to do the same for all of the others. And as we're on Excel, I can just drag that down. And you can see that the concentration has increased. The concentration has increased as we've put in more sodium dodecyl sulfate. We knew that, right? Because we already saw that the absorption increased, and the thing that's changing is the amount of aspirin going in. So we know that there's more in there because it's absorbing more light. So this is for the diluted sample. So remember, we took the saturated solution and we diluted it 3 ml to 10 ml, and then we took 0.5 ml of that and diluted that to 25 milliliters, which is roughly a dilution factor of 150. It's not exactly. So if we say the first part was the dilution of 1 in 3, and then the second part of 1 in 50, 3 times 50 is 150. I know it's not exactly that, but that's what we're just going to go with roughly here. And so to get to our original concentration, we need to times this dilute concentration by the dilution factor. So that's easily enough done. So that equals the dilute concentration times the dilution factor. And so we've got 3,636.36 recurring milligrams per litre is the saturated solution of aspirin in deionized water. And again, going up for the other solutions as well. So you may more commonly see things reported as milligrams per milliliter rather than milligrams per litre. And so if you wanted to do that as well, we could simply divide this answer by 1,000 to get this to milligrams in 1 milliliter. This is essentially number of milligrams in 1,000 milliliters because it's a litre. And so to work out how much was in 1 milliliter, we just divide it by 1,000. And you can see the answer there. So we can see that it's not incredibly soluble. We only get 3.63 milligrams per milliliter. I think that's slightly over what the actual value is. I think the actual value is closer to 3 milligrams per milliliter in water, but of course that depends upon various factors like temperature and also just the error in what I was doing in the lab. And we can see that the saturated solution had more aspirin in the more sodium dodecyl sulfate we put in there. So it's giving an environment for more of that aspirin to dissolve. The last thing that you needed to do was then also to determine its classification of solubility based on the British Pharmacopoeial standards. So you'll also see things written down when you look at drugs or look at anything really that's going to be dissolved, whether it's very soluble, slightly soluble, or practically insoluble. This is the definition of what all of that means. But this is defined as the weight of solvent in grams required to dissolve 1 gram of material. Now we're working with water, so the weight of solvent in grams is directly equivalent to the number of milliliters that is used. 1 milliliter of water is equivalent to 1 gram. And what we've got here is we've got the solubility in milligrams per litre. And we need to know how many litres of water are required to dissolve 1 gram of materials. So we need to know how many milliliters of water because we're working in grams. So let's stick with the milligrams per milliliter. So the way we would do that is if we just take this value here, so 3.63. So we've got 3.63, and that is the solubility in milligrams per milliliter, or in other words, in milligrams per grams. And we want to know how many grams we would need to dissolve 1 gram
of the solid. So we need to convert this to grams. So we need this to be in grams per gram. And we do that by dividing by 1,000, because we're going from milligrams to grams. So we've got 0.00363 grams per milliliter or per gram of water. And so then to work out how many grams of water we need, we then have to do 1 divided by this. Oh, if I could write it in properly. And that tells me that we need 275 grams of water to dissolve 1 gram of aspirin. Now, where does that put us? That puts us in the slightly soluble range, because we've got between 100 and 1,000 grams of solvent required to dissolve 1 gram of material. There are lots and lots of ways of working out, of getting to that same answer. So pick a way that you find works for you, and that's absolutely fine. If you just as long as you get to the same answer. The amount of grams, or in our case milliliters, if you want to say it that way, of solvent required to dissolve 1 gram of the aspirin. So to take you through that again, we had milligrams per milliliter or milligrams per gram here, because they're the same thing with water, and that was 3.63 milligrams per gram. And we want to know how much solvent is required to dissolve 1 gram of material. And so the best way to do that is to get this in grams. Well, the way that I do it, sorry, not the best way, is to get this in grams per milliliter or grams per gram, which is simply done by dividing by 1,000. And that tells you how many grams you can get into 1 milliliter of solvent. And we want to know how many milliliters you need for 1 gram of solid. So we do 1 gram of solid divided by however much goes into 1 milliliter, and that will tell you how many grams or milliliters of water you need to dissolve it in. And in this case, it's 275.5, which is between 100 and 1,000. So we can say that aspirin is slightly soluble in water based on this data. So not very soluble at all. So what does that mean for practice then? So I'm going to stop showing my screen, and you can go through that and do that yourself as well. So in practice, that means that if we want to get somebody to take a liquid form of aspirin, we might need to have something in there to make it more soluble, or we would need to go with a suspension, for example, because a suspension isn't dissolved, it's simply suspended through, and you'll be doing suspensions in the next lab. So looking at your lab script, you'll be able to see that, as I said, the solubility of aspirin isn't very high in water. So for a liquid formulation, we know we're already going to have these other things in there to increase the solubility. We already know they're going to be there because it's already been dissolved. However, you may also see dispersible forms of aspirin. So whereas you get a tablet that you just chuck into some water and it dissolves quite quickly. So in that tablet's going to have to contain the full liquid formulation. It's not just going to be aspirin and some filler. There's going to be something in there, potentially sodium dodecyl sulfate, that will increase its solubility. And so depending on what you're going to be doing with that tablet, it's really important that you use the right formulation. If someone's just going to take it and swallow it whole, they probably don't want the dissolvable formulation because it will start dissolving in their mouth and taste horrible. Whereas if they're going to be taking it as a drink or gargling it maybe for a sore throat, they may want the dissolvable formulation. Equally, like in the example in your lab script, if someone's being fed via a tube and they're prescribed aspirin and you just give normal aspirin, not dispersible aspirin, they're not going to be able to crush that effectively and get it into a liquid to put down that tube without blocking it maybe. So there may be more advanced things than you're doing at the moment, but you can see how understanding this basic principle, aspirin's not very soluble in water, so we need to put an excipient in there to increase its solubility, whether it's in a dispersible tablet or already a liquid. You can see that that's very important for making sure that people get the most out of their medications. So you're also going to be sent a link after this lab's gone out, to complete some short multiple choice questions afterwards. There will be a little disclaimer at the front of those questions explaining that the data from those, seeing as a cohort how well you did on them, I'm going to be looking at and analysing a little bit just to see how well, how much you're impacted, I suppose, by having to do online labs instead of having them face to face. And I'll be comparing that to last year's, how they did with the same questions. All anonymous, so you don't need to worry about that, but just need you to tick to say you're okay with me to just have a look and compare you to the previous year as a whole, as a cohort.